Hi, my name is Dylan Eaton. I'm going to be talking about my problem 3, which covers topics 7 and 9. So it's talking about a rocket-propelled car traveling at subsonic speeds that shoots compressed air out of the nozzle in the back of the car, and out of the nozzle, the air travels into a porous media. So to start this problem, the Mach number needs to be found. So using the relationship of the temperature over T naught, the value of 0.6613 can be found, which can be used on the handout that we were given, and the Mach number can be found to be 1.6. From this, the P over P naught relation can be found. So the exiting pressure from the nozzle can be found from that. And then to discover the flow through the porous media, the Reynolds number equation is used, and that provides a value of 5.79 times 10 to the 6th. So the flow is obviously turbulent through the porous media. Moving on to problem 4, talking about Derek trying to water his garden. The water is flowing through a steel pipe and into a pump that experiences a height change. So to begin this problem, you start with a Bernoulli's extended Bernoulli's equation, and from that you simplify and solve for variable v2, which you get the square root of v1 squared minus 2f. To solve for f, you have to find the Reynolds number to determine the type of flow that the liquid is experiencing. So solving for that, you get a Reynolds number of 2.799 times 10 to the 6th, which is a high Reynolds number, so the flow is going to be turbulent. Using the turbulent friction factor equation, you find that the friction coefficient is 8.283 times 10 to the negative third, but this is not your F value. To find your F value, use the F equation of F equals 4 times the friction factor, L over D, V squared over 2. This yields an F factor of 7.35, and from there the velocity is found to be 6.06 feet per second. To see if the pump is experiencing cavitation, you use the NPSHA equation, and solving for that, you see that the available NPSH is 13.04, which is greater than the 12.5 required, so the pump will not experience cavitation and Derek's plants will get watered. Now on to my 5th question, talking about topic 8, about a BB gun and the BB getting shot out of it, the force drag applied on that. So the force drag equation is equal to the drag coefficient times the area times the density times the velocity squared over 2. So first, to find the drag coefficient, the Reynolds number is needed, and it is found to be extremely low, indicating laminar flow. So the drag coefficient is found to be 0.5, and from there it is a simple plug and chug, and the force drag is found to be 2.237 times 10 to the negative 4th newtons on the BB. Now on to my final problem, problem 6, covering topics 10, 11, and 12. To begin this problem, setting up a continuity equation in the cylindrical coordinate system of the Navier-Stokes, and simplifying, you get that the delta z portion is equal to 0. Now on to the z component cylindrical coordinate Navier-Stokes equation. This all simplifies pretty much down to 1 over mu times delta p over delta r equals 1 over r delta r times r delta velocity over delta r. From here, this equation can be integrated, from which it is found that C1 is 0 using the first boundary condition of where r is equal to 0, the velocity is also equal to 0. Integrating again, you get to the C2 value using the second boundary condition of the outer radius being r naught, where the velocity is also 0. From here, you get a value for C2. Plugging that back into the VZ equation, you simplifies to 1 over 4 mu times the delta P value times r squared plus r naught squared. From here, the values can be plugged in, and then this equation can be plugged into Excel to find the velocity profile of Jimmy's blood, using the radius starting at 0 in the middle and then going negative and then the positive values around that. The reason for this, having a negative radius, is you're looking at the tube, and in the middle you have the radius here, and along the axis it travels negatively and positively, not necessarily a negative radius.